Yeah, I'll get this sign-in sheet going around. So I think we didn't do it last time, right? So just, or maybe we did, who cares? Just to sign in for the 9th, please, and just skip that column that has the purple in it. Okay, so it's that, and then you have to pay real close attention to this next part. This is 1, this is 2. It has an open circle here, and then it comes down, another dot here, comes down like this. This is the point 2, 0. This is the point 0, 0. That's it. That's the whole thing. Here's the picture. They want you to come up with the piecewise function that draws this. So do you understand what it wants? It wants f of x equals, and then a brace, and then the 2 or 3 pieces, however many pieces it's going to take to draw this. So how many pieces do you see? 2, this one, and then this one, right? So let's talk about this piece right here. This is a line, right? This is a line. What is the slope of this line? The slope, -1. Everyone agree? So this right here has a slope of -1. Do you know where it hits the y-axis? At 0, so it has a y-intercept of 0. Now remember, when you're talking about lines, equations of lines, one form of an equation of a line is y equals mx plus b, where m is the slope and b is the y-intercept, right? Y'all follow? So if I plug in m is -1 and b is 0, that will draw this line, right? But I have to restrict it because it doesn't keep going, right? It doesn't keep going. It stops here at 0. So I'm going to put here, what would I get here? If I replace this at -1 in front of x and -x plus 0, just -x, right? So y is -x. So this will be -x if, what though? Your x value is what?
X is less than or equal to 0.
Less than 0 or equal, because what happens at 0? You have a solid dot right down there. X is less than or equal to 0. All right? No questions? Then we switch. Now we switch to a different piecewise function, which is this one. What's the slope of this line? Same thing again, right? -1. But our y-intercept is different. Where does it hit the y-axis? 2. Now it actually doesn't hit because there's an open hole here, but that's where it would hit if it continued. So b would be 2. So the equation would be -x plus 2, wouldn't it? If I were to put it in this form. So that should be the second piece. -x plus 2. But this is only if x is what? Bigger than 0.
Greater than 0, but less than or equal to 2.
Less than or equal to 2. So x must be between 2 but bigger than 0. I'm just going to put a comma here instead of if. Does that make sense?
Could you put that, explain that again? I was like,
Okay, yeah. So you're okay with this? Okay. So where does the graph stop? Because they didn't have an arrow, the biggest x value we could have is 2. And then so x has to be less than or equal to 2. But it also has to be greater than 0, and it can't actually be 0 because then that would be filled in solid. So I have to say strictly greater than 0. Make more sense? Okay. Yep. So that would be it right there. That's the piecewise function. I'll entertain one more if anyone else has a question. Same page. Everybody signed in? or I'm sorry, same section is what I meant to say. 55. Oh, a word problem. Okay, let's take a look at 50. I'm not going to write 55 word for word up here. I'm assuming all of you own a book. You may not have it, but I'll read it. Cost of transporting goods. A trucking company transports goods between Chicago and New York, a distance of 960 miles. So Chicago and New York. $960. I'm just putting information down visually for myself here. I've never done this problem, so let's see how it goes. The company's policy is to charge for each pound, what is that? For each pound, this per mile. How much is that? 50 cents, right? That's 50 cents? Okay, so they're going to charge for each pound that much per mile for first 100 miles. And I'm going to put here per pound. 50 cents per mile for the first 100 miles per pound. Then 40 cents per mile for the next 300 miles. 40 cents per mile for the next 300 miles, right? And that's per pound again. And then 25 cents per pound or per mile for next 400 miles. There is no charge for the remaining 160. So 0 for the remaining 160 miles. Okay. First, graph the relationship between the cost of transportation in dollars and mileage over the entire 960-mile route. So they want us to graph a cost function, basically, that represents how much we're going to pay for whatever miles we go for this entire trip. This is going to maybe look like a piecewise function. We'll see. Everyone understand the problem then? Okay, so that's what I've got. So let me draw here. Let me make sure I read this carefully. Graph the relationship between the cost of transportation in dollars and the mileage over the entire 906-mile trip. So we're going to say miles here, and this is going to be cost. We know the total mileage is 960, right? What's up? Do you have a question or?
You just came back in and I was explaining what,
Oh, okay.
what you're doing.
Okay. So how much is it going to cost us? And see, here's the thing. We don't know how many pounds we're shipping right now, right? This is all per pound, right? So let's just say, for the sake of just getting our heads around the problem, that we're shipping 1 pound. So that way this will be easy math to begin with. How much is it going to cost us for the first 100 miles? 50 cents per mile. So, and we're going 100 miles. So how much is that going to cost me?
$50.
$50? How are you getting it?
Multiply 0.5 times 100.
So it moves it over twice. So you get 50, right? So it's going to cost us $50. So I'm going to put here $50 for that first 100 miles, right? That's what it's going to be. Yes? Now, if we go short, also I should not draw solid because that's not what it is, right? As far as if I go 50 miles, is it going to cost me $50? No, right? How much is it going to cost me to go the next 300 miles? So that'd be 100 to 400. So how much am I going to pay to go this next?
120.
So you're doing 300 times this,
Yeah, so
which would be
120 plus the initial 50, so
120.
70 total.
So how do we want to do this? Do we want to, when we get to 400 miles, we know that we're going to pay this much more, but we already paid 50. So you want to tack it on top?
Yeah.
So it'll be the 50 we started with, which would be here, but add 120,
Yeah,
which would put us where?
170.
170? Understand? We good? And then what? 400 miles. The next 400 miles would put us out at what? 800? And how much will we pay for that? 400 times this would be 100 bucks. So now I'm off my chart because I'm going to take the 170 we already paid. I'm going to add to that, so we're going to be up at what? 270. And then for the remainder of the trip, it's free. So at the end of the trip, I'll be here at what? Still 270? So if I ship 1 pound, that's how much it's going to cost me. Agreed? What if I ship X pounds? 270 times X. Because this, instead of being 50, would be 50 per pound, wouldn't it? So if I just ship 2 pounds, this would now be 100. If I ship 3 pounds, this would be 150, right? So everything just gets multiplied by X. So at the end of the trip, at the end of it all, right, you should have 270X is the total cost. Do you agree? For X pounds. That's what it would be. Now, the next part says find the cost as a function of mileage, which is what we have here, for hauls between 100 and 400 miles. So now we're saying instead of going all the way from Chicago to New York, what if you only are going to go somewhere between 100 to 400 miles? Can you tell me how much you're going to pay? I mean, we know if we go the whole way how much it's going to be, right? 270 times X. But what if somewhere in here we're stopping and that's all we're going? Can we find the cost as a function of mileage? I'm going to start this kind of over.
Be basically trying to find the slope of the line, would you?
Well, maybe that's one way we can interpret it. If we're going to go between 100 and 400 miles, right? If that's what it says for part B. The cost if we're between 100 and 400. So if you're only going to look in here, this is very tricky, so let's try and pay attention, all right? We definitely are going to go the first 100, right? So the first 100, how much are we going to pay?
50X.
50, right? Just 50. Well, if we're going to say X is the pounds. Let's again, this is miles. This is cost, right? And let's let miles in our cost function, let's let it be M. So we're going to say like the cost is a function of miles. We know for sure if we're going to go between 100 and 400 miles, so I'm going to put a domain restriction here. M is between 100 and 400 miles, then my cost is going to be this. Definitely the first 100 miles at 50 cents per mile, which we said was $50. That's going to be a fixed cost, right? That's never going to change if I go at least 100 miles. So it's going to be 50 plus, now this is the part that's tricky. Let's say I only go 200 miles. Let's say that's how far I went. How much am I going to pay for this piece? How are you getting 40?
Just multiplying that 24 cost per pound by 100.
By 100, right?
Yeah.
By 100? Because that's how much further you've gone. If this was now, instead of 200, if we had gone, let's say 250, then it would be 0.40 times 250? Times 150. See, this is the part that you have to account for. M is how many miles you've gone total, right? So isn't M 250? Yeah. But to get how much it's going to cost in here, I don't want to multiply 0.4 by M, right? I want to multiply by what? M
Minus 100.
take away 100. So watch the way I'm going to write this here. It's going to be 0.40. I'm going to run out of room. Let me move this over. The cost as a function of M is going to be the 50 plus the 40 cents, right? Times, not M, but M minus 100. So now if you plug in 250, right? You're going to spend the 50 bucks for the first 100 miles there, and then you're only going to pay 150 miles, which is this, right? At the 40 cents per mile. Yeah? Now distribute. Here to here, here to here. And I'm going to put the 0.40 M out front. And what's this times 100? Minus, or negative 100? Minus 40, which is going to then add to 50 and become 10. This is it right here. If you go between 100 and 400 miles, then all you have to do is plug M into this, and that'll give you your cost for the trip.
And then the C pretty much do the same thing.
Pardon? And for C, the difference is that you're going to have a fixed cost for this and this. So your constant's going to be different. And then this last piece, if this right here is M, then it's going to be what? M minus 400.
Minus 100.
Nope. Nope, because this 400 accounts for this 100 already, right? So minus 400. Hope that makes sense. Part C, I'll tell you what the answer for part C is. For part C, I'll let you do it on your own. It's 70 plus 0.25x. Or you could write it the other way around. Questions? All right, let's get to today's stuff. See, these are the things that I was trying to tell you, last class. You got to be careful in this class because that problem is fair game on a test because it's in your homework. So if you have any questions over these homework assignments, you need to make sure you're getting with me, getting with tutoring lab. Okay, you don't want to be like, well, you never did anything like this in class. Well, it's on your homework so that you have the opportunity to ask questions, clarify the concepts. And if, the thing is, I'm not going to go outside of your homework or outside of the lecture and pick problems I never assigned you or never showed you. I won't go outside of that. But if I'm going to promise you I'm not going outside of it, then you're accountable for the stuff that is presented. Understand? Okay. All right. We're going to move on. We were looking at piecewise functions last time, right? We started talking about it a little bit, and I just thought I'd show you this one example just to make sure everybody kind of understands what's going on. I think I'm going to kill the lights a little bit because it's hard to pick up. There we go. So here's the piecewise function, negative 3x if x is less than or just less than negative 1. 0 if x is equal to -1, and 2x squared plus 1 if x is greater than -1. So you have 3 pieces, right? And so what I've done is I've graphed all 3, and I've color-coded them so you can see them, right? You have y equals -3x, which looks like this. You have y equals 0, constant 0 function. And then you have that parabola, y equals 2x squared plus 1 right there. But because we have domain restrictions, this -3x is only drawn to the left of x is -1. So if I go ahead and, I think this is the one. See, this is x is -1, right? To the left of that, I only want to draw this guy right there. So I only want to draw that piece, right? And then in the second interval, which is x equals -1, I want 0. So that's actually going to be at x is 0. Where the heck is it? Oh, at x is -1, pardon me. At x is -1, it's 0. So here's x is -1, and I just want to put a dot right here. That's all I want to do. So that's this right there. And then on the second, the last piece right here, which is the parabola, is this green region. I want to graph that. And then I'm going to take all this shit out of here because it's just confusing. I think I've got it all there. That's the graph of the piecewise function. So it's a line to the left of -1. Until you get here, then you have to jump down, put a dot. Then you go back up here, and you draw the rest of your parabola the rest of the way. See how that all fits together? Okay. So if I were to give you a piecewise function, I would expect that you could graph it. And if I give you the graph, it would be more like the one that was asked, where there are lines, because those are easy to pick up, like what the slopes are and things like that, and then you paste them together. So any questions on this?
I have a question.
Yes?
Where the blue and the green line meet, you have an open circle?
Yes.
Is that because y equals 0 on the bottom?
That is because this line is not defined at -1.
Okay.
See the greater than, not equal, and then this one's greater than, not equal. So the question is, what's happening at -1? Well, at -1, we want to be 0. So that's why when you get to -1, you don't fill that in. You actually come down here and plug in at 0, you put a dot. Okay. We got a lot more graph stuff to look at. Here's the next one. All right. So 3.5 is the next section. And this is graphing techniques. So if you recall, last class what I did was I introduced the idea of this toolbox of functions that we all should know. All right, we should be able to just, oh yeah, sure, the square root of x looks like this. Absolute value of x looks like this, right? We have all these functions in our mind. Now what we're going to do is we're going to use basic properties to be able to create transformations of those graphs. And the first thing we're going to look at are vertical and horizontal shifting. So let's see how this reads. If y is some function of x, so notice, I'll just highlight this. If y is some function of x, and you know what the graph of f looks like, so f is something you know. If you add a number to it, what is it going to do to the graph? It makes it go up. If you subtract a number, what's going to happen? It's going to go down. What if you add, I put in here, you add h. What's the difference between this one, adding h like that, and adding k like that? What's the difference between those two? It's in the parentheses. The h is in the parentheses, and the k is outside. So let me show you an example of the difference of those two. I'm gonna ask everyone to remember what this function is. What does that look like? It's your v, right? With the sharp corner? Yeah? We all know we can just draw it real quick if we needed to. All right, compare that. I'm going to say f, I'm going to put 2 down here, just because it's a different function. It's not the same thing. Plus 2. And then f3 down here which is going to be this. Okay? So the first function up here is comes from our library, right? Or the toolbox, right? We know what that one looks like. This one, the 2 is being added outside the absolute value. So this should move that picture that we know, it should move it up 2, shouldn't it? And this right here, because the 2 is being added inside the function, right? That's inside the absolute value. This should have the effect of doing what? Left 2. Now, your instinct, adding 2 up 2 makes sense, right? Because positive is up. When you add 2 inside, your instinct would probably make you think adding is positive to the right, this way. But it's actually opposite. All right? So when you have shifts that are horizontal, they're opposite of what you think. Vertical shifting is what you think, what naturally, positive up, negative down. Right? So let's see how quickly I could graph these. That's F, isn't it? Okay, move up 2, take this whole picture, move every point up 2, and it would draw the same picture like that. That's F1, or sorry, that's F2. That's this one, isn't it? And then this one would be the original picture moved left 2. So, pardon?
It's white.
It's not wider, no, because all we're doing is moving it, translating it. When we do translations, it's just up, down, left, right. Nothing is going to widen. Not yet. We're about to do that. So it's just going to be like this. This is F3. Understand? Vertical and horizontal shifting is the most basic type of shifting that you can have, transformation. But they're useful. All right. And if this were a -2, of course, we would go to the right 2. If this were -2, we go down 2. What's nice about this is that this works for any function that you know what it looks like. So when you get to pre-cal, and you're talking about sine curves and cosine curves, this all applies. You can move them around, doing the same thing. All right, now we have what's called stretching and compressing. So this gets a little weird, so let me do this with an example. I'm going to show you this same, let's just stick with this one. This is our library function, and we're going to compare a couple. First, I'm going to say f sub 2 of x. Let's do the first one. We're going to multiply by a number in front. A, you see the number in front of the function? And that a is going to be bigger than 1. So how about I put like 2 absolute value of x. And then the next part says, what if I take a number in front that's between 0 and 1? So what about 1/2? It's between 0 and 1. And then the third one, well, we'll get to the third one in a second. Let's just look at those two. So you start out with your library function, which is this absolute value function right here. All this does, this one, is doubles all your answers. These are your y outputs, aren't they? You plug in an x, it spits out this for y. Now I'm supposed to double them. So what is the y value right here? What is your y value on the original function right here? What's the y value? 0. What's 2 times 0? Still 0. Okay, what's the absolute value function, this one, at 1? It's 1, right? Now double it. It's going to be 2. So instead of being here at 1, it's going to be up here at 2. And the one out here was 2, right? You plug in 2, you get 2, but now you double it, you're up at 4. So what this does is this, right? And if you go to the other side, it's going to be the same thing, like this. This is f sub 2. Do y'all see that? So what do we call this? It depends on how you want to look at it, actually. Someone could say that I've stretched it vertically, that I've taken these 2 points, like these 2 arrows, and I've pulled them up, which made the effect of doing this, right? So I've stretched it out vertically. Someone else may say I've compressed it horizontally. I've taken this and I've smashed these in and made it horizontally compressed. Those are pretty much the same. Vertical stretch is basically a horizontal compression. Understand?
But technically, that would be a stretch. I guess that's what the book would say.
I'm not sure what. Let's see if they identify which one. Shifted. Vertically stretched is what they call it. Yeah. So that's where I said the first way I said you could stretch it out. Now, if the number in front is bigger than 1. If the number in front is between 0 and 1, what does it do? It's the opposite, right? Like if this was supposed to be a 1, now it's half of that, so we're here. If this was supposed to be 2, now it's 1, so now we're here. So it has the effect of drawing this.
So it's a vertical compression / horizontal
Stretch, yeah. This would be like you're taking it vertically and compressing it, which smashes the edges down. Understand that? These are hard for me to test you on because it's hard for me to see vertical stretches and compressions. It's hard for me to see that in pictures. But you just need to understand, you need to get the idea of what's happening. All right. Now, what if the number that you have is inside? So let me show you those. I'll put those here. F4. So what if you have in here 2x like that? Well, let me have the original one up here. Get all these others out of here. I'll just draw a whole new one. Okay, here's the original one. Like this. So what does doubling inside do? Double.
Like the X and Y, should they both be double?
I don't know, would they? What do you think? Just try one. Give me a value of x right now. You want 5? Can you be a little closer?
Okay, 2.
Okay.
1.
All right, let's go. Let's start it in the middle. Why don't we start there? Plug in 0. What do you get? 0. So we're still here, aren't we? So this doesn't have the effect of moving it up, down, left, or right. But now watch. When we plug in 1 now, this is actually what? 2. So when I plug in 1, I'm actually, instead of being up at 1, I'm actually up at what? 2. Now what happens if I plug in 2? When I plug in 2, I'm actually at 4, right? Absolute value of 2 times 2 is 4, so I'm up here at 4 instead of 2, yes? What about the negatives? What happens if I plug in -1? So -1, what happens? This becomes -2, absolute value is 2. So instead of being -1, 1, we're at -1, 2. And then if you plug in -2, you'll be at where? -4, absolute value. So you'll be, instead of 2, you'll be up here at 4. What happened? What does that look like to you?
Vertical stretch.
Looks like a vertical stretch again, right? Or a horizontal compression.
It looks like the same thing as the 2.
It looks like this one, right? Doesn't it? It looks like this one. In fact, they're identical in this case because of the function itself. But
Because there's nothing added or subtracted at the end, right?
you could pop this 2 out of the absolute value with the property of absolute values, but the idea is this. If you put a number in here in front that's bigger than 1, it's going to do a horizontal compression, which is almost like a vertical stretch. Now, what if the number in front is smaller than 1, but bigger than 0? What do you think there? It's going to be I'll do it this way. Horizontal stretch. All right, so let's plug in a number that we know we'll get a nice value out of here. How about 0? Okay, 0, we're here again, yay, we're still at the origin. But now let's plug in a nice number here. How about 2? When we plug in 2, what's half of 2? 1. So when I go out to 2, instead of going up to 2, I'm going to actually only go up to 1. And the next nice number that I can plug in here would be like 4. Half of 4 is 2. So when I go out to 4, instead of being up here at 4, I'm actually only at 2. Make sense? So we get this right here, like this. And we go the same thing the other way. So that one, this is actually this one. They don't match by color here. That one was a horizontal stretch, which you could also almost look at as a vertical compression. Right? Okay, let's talk about reflections. If you put a negative number in front of a function, we're going to stick with this one. If you put a negative in front of a function, it has the effect of reflecting it over which axes? It says it up there. X-axis. Let's see if that makes any sense to you. If this is the original function right here, then to say that it's reflected over the x-axis means that it would look like this, right? And that's because everything that used to be positive, every y value that used to be positive, is now negative, isn't it? Every positive y value is now negative. Every positive is negative. 0 is neither positive nor negative, so it doesn't move. So do y'all see that? Everything just flips. Now, if you happen to have a function that was down here already, like this, what's a toolbox function that would have both positive and negative parts to it? X cubed, good. X cubed looks like this. That's x cubed. Negative x cubed, so negative in front of this, would look like that, wouldn't it? Because it would bring this part that was negative up to be positive. It would take the part that's positive and take it and flip it down over the x-axis to become negative. So that's a reflection over the x-axis also. We good? Yes?
So on X cube, when you do like vertical compression and stuff, so I guess it would just kind of get tighter in or...
What would happen if we tried to graph? You want to just look at maybe like 10 x cubed? What that does is it takes every value and multiplies by 10. So what I like to do is imagine that this, whatever this value was, let's just say it was, I don't know, y, right? It's now 10y, which is way up here. So it's like taking that point and dragging it up here, and all the other pieces come with you. And so it makes it much steeper, right? So it's stretched that out. Do you see why you can look at it as a stretch? And then this piece over here dives down faster. But see, it's hard to draw that unless you have really like graph paper and or you use a computer. Yeah. Well, I think I have this all here. I can mess with it myself. So like, you want to see x cubed? There it is. Let me move it around. There it is. There we go. There's x cubed, right? And then if I want to, I can stretch it out in front. Let's see. Just watch it. Let me make it a little smaller. There. If I stretch it, see it? Now the original x cubed is the red one. You see it? That's the idea. I have this set up so you could do all the different basic functions. So there's the cube root of x, right? And so what if I put this? Let's talk about what this would be. If I asked you to sketch this. So this is an example. I want you to sketch. Why don't you take a minute to try and do it yourself? I want you to sketch f of x equals 2 cube root of x minus 2 minus 3. I'm going to see if you can sketch that. This should not be a 20-minute problem. This should be about a 3-minute problem at the most. And if you're having trouble sketching it, at least do this. List the transformations. In other words, tell me, even if you can't draw it, tell me what sorts of things are going to happen. Okay, like it's going to move this way by this much, and try and give me verbally or a list describing what's going to happen. If anyone thinks they have it, let me know. I'll come by and take a look. Think you got something? It's all right. So, right 2, down 3, vertical stretch. Yeah, okay. I'll have to verify with the picture, but I think that's going to work. Who else?
So what this you go right twice, compress it by 2.
If you multiply by 2 out front, it's going to do a vertical stretch. Let's make everything taller. Because vertical compression would smash everything down. Okay?
But what about everything else? Was it right about everything else?
Yes, everything else is great. Yeah. Vertical. Down 3. Yeah, that looks right. Okay. You got some? I think most people are getting it. Okay. I think most of you are getting it. So let's talk about these transformations. First of all, what's the toolbox function? Everyone has to recognize this is the cube root function, which we know what that looks like, right? It's just a matter of all the different things. So let's list them out. You tell me. Just let's have volunteer. Go ahead. Give me one of the transformations.
You had -3, taking it down, it shifts down 3.
Okay, down 3. Anybody oppose this? Down 3? Everyone's on board?
With the -2 that's inside the cube root, that would mean you would move to the right 2.
Right 2? Anyone disagree with that? Okay, you want to give me the next one? Go ahead.
And it's going to multiply all of the outputs by 2.
Okay,
2
so
out in the front.
that would be, what kind of transformation is that? Horizontal compression or vertical stretch, whichever way you want to look at it.
I think it would be easiest to just look at which way it's stretching.
It's different for everyone. And no matter how many times I've covered this section, everyone sees it kind of a different way. So vertical stretch by a factor of 2. So we have 3 basic things that happened here, right? Everyone's on board with that? Here's my question to you. Does the order in which you do these transformations matter?
Yes.
Yes, maybe? What do you think? Let's take a vote. How many of you think the order that we do these matters? How many of you think that the order we do them doesn't matter? And anybody not care? Okay. Okay, so it looks like we've got some different opinions on this.
I mean, like, if you were asked to do like a certain set of like transformations in a specific order, then they would matter. But if we're just trying to figure out like what different transformations are done in just one problem that already has in place, then
What I'm getting at is if everyone agrees these are the transformations that appear in this problem, then if I start to take that picture and start moving it around using this, does it matter if I do the down 3 first, then the right 2, then the stretch, or can I do the stretch, then the right 2, then the down, or can I do the right, then the stretch, then the... Does it matter?
Right now, it doesn't look like it does matter.
Most of the time it doesn't, but sometimes it does. And because of that, we have to use order of operations to be safe. Now, do you remember order of operations? You do parentheses, exponents, multiplication, division from left to right, addition, subtraction from left to right. Yes? So what you want to do is look at this. And when I say order of operations, it's a little confusing because you're like, what do you mean? There's this. I can't evaluate this because I don't know what x is, right? But let's imagine that you were x. If you were x, the first thing that would happen would be this, right? Which means you're going to do this first. I'm going to list these in the correct order to do them in. After you do this, what comes next? The cube root. The cube root is going to give you your basic shape, which we knew from the beginning of the problem, right? We knew what this toolbox function was. So I'm not going to list that as like the next step. But after this, are we going to do the times 2, because this is multiplication, or are we going to subtract 3? We're going to do multiplication before subtraction, aren't we? So the next thing would be a stretch, and then finally followed by the down 3. And I'll try and give you an example of one where if you do it in a different order, it will give you a completely different graph. All right? I'll give you an example after I do this one. Okay, so here I go to sketch this. If I'm sketching this on a test, here's what I would do. I would start out by very lightly with my pencil drawing cube root of x. That way my instructor knows. And by the way, on the test, I will ask you, what's the toolbox function or what's the library function? I will ask you to list out the transformations in correct order. Then I will ask you to draw me the picture. So I would like to see that toolbox function in there. And then you can just give me your final answer. But it's nice to see like maybe one point get moved around here. So first thing I'm going to do is write 2. Right? That's where I am now. And then I stretch. Now the stretching is the next thing to happen, but it's hard to draw it right now. If I were to stretch it, it would probably look more like this now. Would you agree with that? I've taken this picture and I've stretched it out like this. So there, I moved it to the right 2 and I've stretched it. And now, down 3. So take this dotted picture and just move it down 3. 1, 2, 3, and that puts you right here. And now draw it nice and solid like that. That would be good enough on the test.
When you want us to do the stretching or compressing, does it need to be very accurate?
It does not need to be accurate because the whole idea of this is to be able to quickly sketch. And if we're sitting here taking our time to like draw points and then it defeats kind of the purpose. Yes?
Are you going to want us to show that order of operations in our work in sketching them?
No, only when I ask you to list them. I'll say list them in the proper order.
So if you do not ask us to list it, then we can just do a quick dotted sketch of the toolbox function and then our
Final picture, yes. Okay, so let me try and give you one that the order will matter. Okay? All right, what's the toolbox function here? I'm using the word toolbox and library the same, right? Because in different books they call them toolbox functions or library of functions. And
Square would be a problem.
okay, so it'd be the squaring function, right? So the toolbox is x squared, which we call the squaring. If you write x squared, that's fine. If you write squaring, that's fine. All right, let's list out the transformations in order. So what's first?
Left
Left 3?
Directly on the.
Because that's inside here with the x, right? Adding 3 sides. So left 3. Next thing.
Reflection over the x-axis.
That negative is like a -1 sitting out front. Negative's in front of the function, flips it over the x-axis. Reflect over x-axis. Okay?
Move it down 5.
Down 5. That would be it. That would be the order. Okay? So let me try and draw this real quick. So I start out with the squaring function, which is this. I move it to the left 3, which is this. I reflect it over the x-axis, which is pivot the whole thing downward. And finally, down 5. So this whole picture comes down 1, 2, 3, 4, 5. Here we go. And it goes down like that. Let's try it a different order and see if we get the same answer. So I'm going to do it intentionally to make it mess up, all right? I'm going to do this first. I'm going to go down 5 first. Okay? That means I start with this, right, and go down 5. 1, 2, 3, 4, 5. I'd be right here. I'd be up like this, right? Now what do you want me to do? I'll let you choose the next two.
Left 3.
You want me to go left 3? Okay, 1, 2, 3. So now I'm here, right? Now what? Flip it over the x-axis. Here's the x-axis. It flips all the way over like this and comes up here like this. Do you see that? It doesn't flip over this. That's not the x-axis. The x-axis, right? This point right here has to go right there. You see that? So it's dangerous.
Well, technically, wouldn't it be? Oh yeah.
Like if this y value, right, is -5, now it's going to become +5.
So if you started out like reflecting it over the x-axis first.
If you reflected over the x-axis, then moved it down, then moved it over, then you got lucky, yes.
So should you start with reflection first, regardless of whatever the operation?
Should it start with reflection first?
Let's say like,
That's not so much the issue. It's this right here can't be first. But the thing is, if we have a systematic way of approaching it, we should use it. And that's why the order of operations. Start from the inside, work your way out. If you follow that list, you should be okay. All right, well, shall we, we didn't look at any of these. We don't need to, right? There are some examples. I think we can handle that. Sketch this. Hold on. We do need to talk about those, but I'm just trying to see where we need to go with this. Okay. You want to try that one? Try D. See if you can do D. You should be done. You done? No, I'm kidding. Pardon? Anybody there yet? No? I'll draw mine on the board while y'all are working on it. There they are. Toolbox function, move to the right 4. 1/4 of it's going to vertically compress it or horizontally stretch, and then just move that whole thing up 5. Okay? That's it. All right, now things are going to get a little weirder now. All right, let's. Oh, what I didn't tell you last time is like why would you want to be able to do this quickly? Okay, let me write down this function. It was called J up there, but I'm calling it F. F of x is 1/4 square root of x minus 4 plus 5. All right. I need a volunteer. Okay. Is it possible for me to plug in a number right here and get out an answer of 2? Yeah, is there an x I can plug in and this will spit out 2? Why?
8.
Can anyone give me a definitive answer, yes or no, and explain why?
No, because it's not in the domain. It's not 4 to infinity, right?
Close, but I'm saying, is there an x I can plug in You're close. Anyone? No, don't erase it, or?
No, it's not, obviously. Because you moved up 5 and then you only keep going up.
Okay, if I look at this right here, what's the range of that function?
5 to infinity.
5 to infinity. Everyone agree? 5 to infinity. That's the range? You can tell by just looking at that. That means, is it possible